Okay, so let's get started. Today we are going to continue our transition from the PPO algorithm that we discussed in the last class to GRPO, which is popular algorithm that was released this year and has kind of allowed us to train reasoning models. So these are models that are capable of producing chains of reasoning before actually answering some prompt. And they're very common for math problems, coding problems, things like that. But if you've interacted with, GPT-5 or any of the frontier models, most of them these days have some sort of thinking or reasoning component. And so the algorithm we're going to discuss today is an example of a training strategy that incentivizes models to reason before coming up with their final answer. So before we get started, the Tinker API keys are now working. I did not change anything. They just started working the day of last class. So hopefully they continue to work over the course of the rest of the semester. But if they stop working, please let us know. I don't know that we can do all that much, but at least it would be good to know. And if you're actively using those keys and you run into any usage limits or rate limits or anything like that, you can also let us know. We can give, we have a few more keys that we can provide in case of any of these limitations. All right, so I wanted to start by kind of just zooming out and recapping all of the stuff we have done in the PPO algorithm, and then kind of move on to what we're going to change in order to get to GRPO. So from last class, where we focused mainly on the PPO algorithm, we have basically these four-ish high-level steps. So the first is we're given a batch of prompts, and let's say there are B different prompts in this batch, so X1, X2, XB. We generate corresponding responses to each prompt, Y1, Y2, YB, from our policy model, which is the model we're currently training. So note that as we discussed this algorithm in the last class, we're only going to be producing one response, Y, for each prompt, X. We will change this when we start talking about GRPO, where now for each prompt we'll produce multiple different responses and use those to compute our baseline. But in the algorithm we discussed in the last class, now for each example, which is a prompt paired with a corresponding response, we compute the reward. And remember that this reward comes from our reward model, which we've already trained and set aside for use in this PPO training step. So let me just make some notes up here about our notation so far. So we have B equals batch size, and we might have L equals the sequence length, max sequence length. So one thing that I wanted to emphasize is that what are like the shapes of these different quantities that we're computing. So we have our rewards, they come at the very end of the response. But then we have things like our policy ratio, our KL divergence. These are computed at the token level. And so it might be a little bit confusing to see all these equations where things with different shapes are kind of getting subtracted or combined with each other. So I want to emphasize like what these shapes actually look like, which I'll do in a bit. But let's say we have our rewards, right? Now we talked about computing the advantages. Oops, compute advantages by subtracting baseline and also the KL penalty that is trying to keep us as close to our SFT model as possible, right? So we had two different calculations here. One is the advantage is the reward minus this baseline term. And now if we write down the shapes of these different things, the reward is just a vector, right? So we have one score from our reward model for every entry in our batch. So we have B total rewards here. But our baseline kind of varies depending on how we implement the baseline. So if we are, so I'll put varies in shape, it could be the same dimensionality if using like the batch mean or some simpler stats, as we'll see in, sorry, just make this more understandable, varies. Or in the traditional PPO RLHF implementation, it would be batch size by L. So every single token in the batch gets a separate baseline score, and that's if you're using the trained value function or critic model that we discussed last time. So let's say we're using the value function. One question is, well, the reward is a vector of dimensionality, the batch size, and our value function outputs something that's B times L dimensionality. So how do we do this subtraction? And this is where I had mentioned that we do what's called as broadcasting. So essentially that reward, the BX1 term, is subtracted. So basically the reward for one example is used for all of the tokens in that particular response. And so when you do this subtraction, you broadcast the sequence level reward to each of the individual token level positions. And so if you were using the value function here, then your advantage will also be B times L dimensional. Does that make sense? So it's basically saying that you're using your reward that you get at the very end of generation of these Ys as a kind of stand-in for all of the individual token level rewards. Okay, the next thing that we did was incorporate this KL penalty into our advantage. As we'll see later today, this is not necessary for you to do. You can put this KL penalty elsewhere. You can also remove it entirely, which is becoming more common these days. But in the standard formulation, we computed this kind of KL augmented advantage here, which is this minus this beta hyperparameter times the KL divergence, SFT. And note that this term here is at the token level, right? We compute this by just subtracting the log probabilities of the token level, log probabilities of our y as computed by our current model minus the same probabilities computed by the base SFT model, right? So this is a B times L dimensional thing. This, if it is batch size times 1 before this computation, we'll do the broadcasting and then subtract this KL penalty. But at the end of the day, this quantity here is also batch size by max sequence length matrix for a single batch. Yes?
But if we're using the mean version for basic.
Yeah, so if we're using the mean version of this, then this advantage here is batch size by 1. And as we'll see, because GRPO is using the mean version of within a group, not a batch, but as we'll see, the KL term doesn't come into the computation of the advantage in GRPO, so it's moved to an external term in the loss. But we'll talk about that later. Yeah. Other questions about this? Okay. Let me check on here. It seems good. Okay, so now that we have this, a term that incorporates our reward, our baseline, and our KL penalty, the next thing that we did was compute our policy ratios, right? And once we do that, we're able to take gradient steps. And so this is another thing that I kind of wanted to go over again, and with a slightly different emphasis, just so it's clear from the implementation perspective how this works. So here, we first defined this policy ratio as this row of I, where I is a position in the sequence, so it's a specific token. And this is the probability of generating that token under our current policy given all of the previous tokens and our prompt. And this is divided by the same probability computed by our old policy, right? Where this theta old is not the same as the theta SFT. Right? Theta old is the model that generated this Y in the first place. So the model that generated the responses in this batch. And the whole point of this policy ratio is that for any given batch, we are going to take multiple gradient steps before we move on to a new batch and generate new responses. And so this policy ratio is 1 before the first gradient step, and then it changes as you perform multiple gradient steps on the batch. So we will talk more about this in a bit, like why would you want to do this? Why can't we just take one gradient step on the batch and then move on to a new one? But I also wanted to highlight a couple other things. So now keeping on with our shape of these different quantities, so in general, when you look at all of the policy ratios, these rows are also of dimensionality BXL, so you have a different ratio for every token and every example in the batch. So you can see how this kind of fits into our advantage with the KL term included. They're both of the same dimensionality, which then allows us to compute this loss. So instead of writing the expectation way, I'll just write it out for a single example here. So we're going to sum over all of the tokens in the response. And we had this kind of clipping and choosing the minimum of these two quantities. So one is the unclipped product of the policy ratio pi times AKL xy. And the other term that we could consider is this clipped policy ratio. I'm so bad at drawing these rows. Okay. And then we had this hyperparameter epsilon that controls the kind of width of this trust region, right? So this epsilon is generally set to something small like 0.1 or 0.2, which means that if our if our policy ratio ever falls outside of some range like 0.8 to 1.2, then it gets clipped to maintain continue to be in that range, and we will multiply this by again this term here, yeah, that's our final contribution to the loss for here, just written out for one particular example in the batch. So if you look at this, and we kind of analyzed this a little more closely in the last class, like different cases of if the advantage is positive and the ratio is this, what happens? There are a couple things that I want to emphasize. So first, the intuition here is that if the advantage is positive, our goal is to increase the policy ratio. Right? Because that means that our new policy is putting more probability on this token in a favored response compared to our old policy. That said, of course, this we don't want to increase it too much, right? We want to increase it, but do a kind of slow, careful update so we don't exit that trust region. And if we do exit that region, then we're not going to perform any more updates on that particular token. Similarly, if the advantage is negative, we want to decrease the policy ratio. So to, on average, lower the probability of all of the tokens in that response. Now, one thing that I wanted to highlight here is that in this PPO algorithm, when we are doing backprop, we're always backpropping through this policy ratio here, right? Where if you look at the computation of the policy ratio, you'll see that the numerator is a function of our current policy model, P sub theta. The denominator, we are not going to backprop through. So this will be kept frozen. We don't want to adjust the old policy model because that's just what we're using as a reference to figure out how much our model is deviating away from what currently generated that batch. Now, if you look at the other terms in this loss here, you'll see that the advantage also includes this P theta through the KL term, right? So the KL term is a function of the P theta and also PSFT. So of course, PSFT we're going to keep frozen. We don't want to update that. It's again a point of reference for us to measure how much we're deviating away from this instruction tune model. But importantly here, the advantage is completely kept frozen. So we are not going to backprop through the KL penalty in the advantage calculation. So basically the only thing that we are passing our gradient through is this policy ratio, specifically the numerator of the policy ratio. Yes? Yes.
So the rho I is being multiplied with like the nth position.
Yes. Yeah, so here when you're, I guess you're referring to the product of the policy ratio and this advantage term. They're both B cross L matrices, right, for a specific example. And so when you do this product, you're just doing the element-wise multiplication.
Like, what was the point of putting in the minimum between the TF value and the actual?
So remember so the question is, what is the point of doing this minimum of the clipped and unclipped objective? In the last class, we went over all of the different cases here, but the high-level idea is that we do not want to make updates past some threshold of the policy ratio. So like, if we have a positive advantage, that generally means this response was good. However, we know that if we just upweight all of the tokens in that response by some huge amount, the model might lose its stability, right? It might be really good on that response, but it might suffer dramatically in other places. And so in general, this reinforcement learning is very, very fragile and brittle. And so all of these different things that we're seeing, like the KL penalty, the policy ratio clipping, they're all designed to make very small targeted updates to the model. So the minimum of the clipped and unclipped thing is intended to only update the model to a certain point, but don't go beyond it and kind of ruin its performance on other prompts and other responses. So it's just kind of taking a very careful approach to the optimization process. Okay, so right. Just to be clear here, our goal is to backprop through the numerator of the policy ratio. The other thing to mention is, again, I just want to highlight this distinction between theta old and theta SFT, because it is a little bit confusing. We have several different points of reference in this whole optimization process. Okay, so let's talk a little bit more about the policy ratio. So initially, meaning before any gradient steps, the policy ratio is set to 1 for all tokens. This is because the p theta old is equal to p theta. So we have not changed our model at all. So essentially for every batch, right, if we go back up to our step 1, we get a bunch of prompts and we use our current model to generate responses to those prompts, right? So when we're doing this in our implementation, the model that we use to generate these responses is set to theta old. And when we are doing these updates, we are going to keep around the probabilities that were produced by this theta old, but we're going to do multiple updates on the model. So our p theta is now going to be different than our p theta old. That's the general idea. So before any steps on this batch, the policy ratio is set to 1, but we normally take multiple steps on one batch. So this is not like what we do in SFT or most other training algorithms, right? For SFT and for pre-training, we have a batch, we compute our loss, we compute the gradient, we take a step, then we move on to the next batch. This is a little bit different. Here, we have our batch and we compute the policy ratio, then we compute our loss, we take a step, we recompute the policy ratio, we take another step, we recompute the policy ratio, we take another step, until we reach some fixed number of steps, which is a hyperparameter. So this hyperparameter is generally set to 4, but you will see like different values, 1, 2, and 4 in open source libraries like TRL from Hugging Face. It's not really clear what the closed labs are doing, how many steps they're taking on their batches, but at least for open models, it's the default value in most libraries is 4. So one question is, why are we doing this? Like if we just take one step on a batch, we don't need this policy ratio thing at all, right? We would simply just compute the probability of this response given our current model, multiply it by our advantage, do backprop one step, and then move on to the next batch. So, if we're interested in taking multiple steps, couldn't we just roll all of those into one big step, maybe with a big learning rate? Can't we just take one step with a big learning rate and call it a day and move on to the next batch? So why don't we generally want to do this?
You might move too far from the model, so you want to take small steps.
Exactly. So if we took one like big step or even normal size step, we are likely to hit a regime where as soon as we update our model, almost all the tokens in the sequence will hit the clipped region the next time we compute the policy ratio, indicating that we might have increased the likelihood of specific tokens in that sequence by like 100% or 200%, right? But we don't know what impact that might have on the model's performance on other prompts. And so in general, the reason why we don't do this is exactly as you say, we will risk taking a step too far in the direction of like either increasing the advantage or increasing probability of positive advantage tokens, but we run the risk of destabilizing our training process. Any other ideas why we might want to do this?
Decoding the particular.
Exactly, that is correct. So let me just write down what he said, and then we'll come back to this. So the first is stability if we take one big step, we will move too far, and many tokens will fall into the clipped region or outside of our trust region. And then exactly what you said is that every time we want to generate new Ys from our model, like every time we have a new batch, it's really expensive, right? So I also want to introduce this term because I've been saying it every now and then without defining it. So the term rollout refers to generating responses with our current policy model. So we have, we have a model that we're training. We want to measure how well it's doing on some new examples. So we have to take some prompts, generate some responses Y from those prompts using our current model. Those are called rollouts. So i.e. generating Y from our policy model P theta are very expensive. And if you compare the cost of producing new rollouts, right? Which requires you to basically use test time decoding, one token at a time, producing new text, right? We're sampling from the next token distribution for each token. This is extremely expensive compared to just doing multiple rounds of backprop on the same batch, right? So kind of the intuition here is that doing multiple updates on the same batch is going to give you more stable and careful updating. So you're essentially more efficiently using that batch compared to taking one update, moving too far, then discarding all the work that you did in generating those rollouts to just go further and start generating more rollouts on a new batch. So that's the intuition here. This process can be further optimized at scale, so you could have kind of asynchronous rollout generation and policy model updating, where then you'll have this trade-off where maybe your rollouts will become too stale, and so you have to manage all of that. There's a lot of papers on this coming out, like what is the best kind of pipeline for reinforcement learning with LLMs, because bottleneck is really this rollout process, especially with long outputs. It can get very slow and consume a lot of memory. And so, we want to make the best use of our rollouts. Okay, any questions about this?
So in practice, when you're doing this in code, you basically generate all of your function, you get your advantage function and all of the other inputs, and then you make like consequent steps of updates.
Yeah.
And in those, when you say p theta old, that's the immediate previous state of the model.
I believe it's the theta old is set to the very first, the model that generated those y's. So not the immediately previous step. Yeah, like if we did 4 steps, our theta old will always be set to the first step, not like if we're on step 4, it won't be set to step 3.
And that would change after every batch.
Yes, that's right. Changes after every batch. Other questions on this? Okay, great. Let me just check on YouTube before we move on to, oh God, what is this? All right. Whoa, that was cool. Okay. So now we've kind of completed our overview of PPO. Yeah.
Do we not have to do like multiple rollouts to do like the multiple gradient steps?
So the question is, do we not have to do multiple rollouts to do multiple gradient steps? I guess what you mean is, given a batch, when we do our first update, why don't we have to do a new set of rollouts? Well, think about it this way, like, we could just take one gradient step on that batch and move on, right? But the idea is that if we take a gradient step, we can then recompute our policy ratios to figure out which tokens do we still have some room to increase the probability of, and which ones should we stop updating, right? So we can get more bang for our buck by doing multiple steps this way and kind of measuring, oh, well, we still have some mileage to go on this token, but these ones we're going to stop updating. So that's kind of the idea. So generally, like with each step on the same batch, we are getting more and more tokens that fall outside of the trust region. Okay, that's a good question. All right, so now we're going to switch to our topic for today, which is transitioning from this PPO algorithm to GRPO. And so I want to give some context, like historical context of this transition before we get into the low-level details. So first, this idea of models reasoning before they predict their final answer is not like one that emerged just this year. There was the very influential paper, I think in 2022, on chain of thought prompting, right? So in chain of thought prompting, you would have a question like a math word problem, and you would ask the model, before you answer, think step by step and produce all the intermediate reasoning components, and only then write your answer out. And we already talked about this when we discussed emergent properties of language models. Like chain of thought reasoning is an emergent property of language models in that as you scale up the data size and the model size, the ability of the model to do chain of thought reasoning and benefit from it in such a way that its accuracy increases on these kinds of math or coding related tasks increases as well. So we know that like if you pre-train a model to sufficient scale, it will be able to do this kind of intermediate reasoning process. However, it wasn't really clear how you could train this kind of behavior, like during the post-training process. So all of the stuff we've discussed so far basically says you have a collection of prompts, and in SFT you have the expert ground truth answers, right? But you don't have the expert's like exact reasoning process that they used before producing that particular answer. That's a lot harder to get at. And as we'll see, a model's reasoning process may not actually look like a human's, right? And you may not want to force it to mimic like some human's reasoning process, but give it more flexibility to figure out what works best for it. The other thing is, as we'll talk about more later in the class, is that like if you're able to train this behavior, you actually have another dimension of scaling up the model. So far we've talked about training time scaling, right? Where we add more data, more parameters to our model, and more compute, and we just scale it up that way. But another dimension that we can scale our model is at test time. So at test time, let's say we can control the thinking budget of our model. So if it's doing chain of thought reasoning, we could say, well, you're allowed to reason for 5,000 tokens, and then you have to produce your answer. What we've found is that as models spend more compute on reasoning at test time, their performance increases. Meaning, and it's not really something that's immediately clear that we can interpret the tokens that they're producing and say, oh, this is why its performance is getting better because it figured out this really complex thing at token 3000 of its reasoning process. It's just more that it seems like the more compute that the model spends at test time, especially for more complex problems, it seems to help a lot. And so getting back to this GRPO algorithm, the first instance of a model that was actually trained for reasoning, like during the post-training process, was OpenAI's O1 model that was released late last year. And so when O1 was released, it really kind of spurred this idea of test time scaling. People were like, oh, well, we're running out of compute and data for pre-training. Maybe we should just focus more on increasing how much tokens the model produces at test time. And there was a few months after O1 was released where everyone in the open source community and at other labs were trying to figure out how OpenAI actually got their model to do this kind of reasoning. There are many theories were advanced, but of course you can't actually try any of them without a ton of compute. So it wasn't really clear. There were some wild ideas being tossed around. And then DeepSeek released this paper, DeepSeek Math, which had a very simple RL algorithm, GRPO, that kind of imitated the same behavior that O1 did when they trained their model. And DeepSeek's R1 model became like the best open weight model that was available. And since then, almost every new model is trained with this kind of thinking and reasoning behavior, not just on math and code, but for all sorts of tasks. So that's kind of where we're going now, and GRPO is the specific algorithm that was introduced in the DeepSeek paper. So, all right, I'm going to first just outline some of the key like mechanical differences here, and then we'll look at how the PPO loss is modified in GRPO. Luckily, we're going to keep a lot of the same machinery that we saw in PPO, so it wasn't a complete waste to just spend like 2 lectures on this algorithm. This one should go faster, and then we can kind of get into more like data-centric ways to view this, because the algorithm is one thing, but the data that you use to train models for reasoning is really important. So we'll get there towards the end of the class. Okay, so one fundamental difference is we're going to completely remove the reward model. And so we talked about how to train reward models on human preference judgments. And we also talked about how a reward model functionally is a pre-trained SFT language model that has been fine-tuned with this final linear layer to mimic the human preference judgments. So this has one positive thing, is that RL gets cheaper. We drop an entire like language model sized chunk of parameters from our training process. It also, depending on how you replace this reward, could reduce reward hacking, which we already noted was a big problem of the standard RLHF reward models. The problem is, and we'll get more into how we do this removal in a way that still gives us a useful reward signal. But if we get rid of a reward model, we can't reliably compute a reward for many tasks. So as we'll discuss a little later, in GRPO, the DeepSeek people also introduced this notion of a verifiable reward, where you have some task where it's very easy to verify if the task was completed successfully or not, right? If I ask you, what is 2 plus 5, right? There's one correct answer. I don't need a giant reward model to tell me if the answer is 7 or if it's not 7, right? So, however, if I ask you, write a great story about a cat with a unicorn, it's kind of unclear how I can design a cheap reward for this task. So this idea is good in many ways for efficiency and for reward hacking, but it kind of reduces the diversity of tasks that we can consider during this kind of training. Okay, the other idea is that we remove the value function, which, remember, we were using to compute the baseline in the PPO algorithm. And we'll replace that with the group mean, actually the z-score. So I should say we remove the reward model, replace with verifiable rewards. I should also mention that technically you can use GRPO with a standard reward model, but that's not the point that we're going for here. We're really going to focus on eliciting reasoning behavior. Okay, and one small technical difference is that from PPO is that the KL penalty is not included in the advantage computation. So, like, we're not going to do this this step over here, where we subtract the KL term directly from this reward, but rather it is going to be included as separate penalty. So we'll see that in the final loss formulation. And now it's often completely dropped. And so there have been many variants of GRPO that suggest completely dropping the KL term has no impact on the performance. It could be something related to the types of tasks that people generally train models using GRPO, and also maybe a function of the verifiable reward, which somehow doesn't allow the model to drift away as much. Okay, so these are some high-level differences. Let's go kind of step by step. Wow, I just like chain of thoughted myself. And we can talk about the exact differences between these two algorithms. So just like PPO, we are given a prompt X, but here in PPO we were generally given multiple different X's, and we would generate one response per X. In GRPO, we're going to be given one X, and we are going to generate a group of G different responses. So these could look like Y1, Y2, YG. So generally this group size is between 4 and 32. So already you can see kind of a limitation of this GRPO training, where in a given batch, you don't have as much diversity over prompts, right? Here you have one prompt, and you have to use your rollouts to generate multiple different samples from conditioned on the same prompt. So we better be gaining something good for wasting all this compute on just a single prompt per batch. And of course, if you have access to more compute, you can have many different prompts and generate a group for each prompt in your response. But like whatever we all have access to, it's generally going to be just one prompt per batch. You could use a technique called gradient accumulation here to simulate the inclusion of multiple different prompts in a single batch, but we're not going to talk about that in this class. However, it could be relevant for your project if you're using this algorithm. All right, so given all of these responses, we are going to compute a reward for each response in the group. And so this will look like X, Y, I. Here we'll see a little difference in the notation. So YI is going to be the ith response generated and conditioned on this prompt. And before we were using I to refer to the position in the sequence. So now we'll switch that up a little bit, because we have now for one prompt multiple different responses, and then each response has multiple different tokens. Okay, so so far not too different other than this concept of a group. But in the third step, we're going to compute the advantage. And here, we've removed the value function, so we're going to use statistics that are computed from our group in order to compute the baseline. So here, compute the group mean and standard deviation. So essentially, we're going to z-score all of the individual rewards in this group, where basically we're going to subtract the mean from each reward and then normalize by the standard deviation. So here, like, we'll compute the mean is just 1 over g times the reward. And then the standard deviation, we'll just call it this, but this is just measuring the variance. I'm not going to write out the equation here. So once we've computed these stats, we're now going to compute the advantage. These we can call the group relative advantages. So for every response in the group, we'll compute this AGR x of yi, and we'll take the reward of that particular response, subtract the mean reward from the group, and then divide by the standard deviation of the group. So here, just to look at the shape of all of these different terms, this thing is a bx1, and so this also is bx1. So so far, we're not going to broadcast this into bxl. That will only come when we do the multiplication with the policy ratio from PPO. Okay, so now what we've done is we have a prompt. We've generated, say, 4 different responses. We compute a reward for each of them and an advantage that is normalized by the group mean and standard deviation, right? So this tells us for any given response, how much better or worse is it than kind of the average in the batch, right? So we could have issues here if, for example, all of the responses in the batch are the same, right? So if I said, or receive the same reward. So if I had a prompt like, what is 2 plus 7? And my 4 responses were like 1, 2, 3, and 4. All of the rewards here are going to be 0, and so I'm not going to get any sort of gradient flow into my model. This was basically a waste of rollouts. So that is one challenge with using this verifiable reward formulation. All right, so the final step here is to compute our loss and do the gradient updates. This is going to be very similar to the PPO loss. So for one particular prompt X, it will first have to sum over all of the different responses in the group. And actually we'll take the average over the average loss over each response in the group. So we'll use I here to denote the index of the response. And then we will use T to denote the token position. So here, this will iterate from 1 to L. And I guess I should have written this on a new page because we have to do all our same clipping stuff. So we'll take the minimum of the policy ratio times our group advantage of X, Y, I. So note that here I can get rid of this T because this group advantage is of shape batch by 1, right? And so here, when we do this product, we're basically going to broadcast that advantage to every single token position in the sequence. So all of the tokens get the same exact score for a particular response in the group, which is in this advantage. And, but, you know, I can just write it out for clarity, even though this is the same across all of the token positions. And we have our same clip, the policy ratio 1 minus epsilon, 1 plus epsilon times the advantage. And yeah, that's our loss here. So we'll note now that our KL term has not appeared here, right? We did not include it as part of our advantage. We didn't want it to mess with the group mean or group variance because we really want that to be a just direct function of the correctness or like whatever other verifiable reward we're computing over the batch. And so here we are going to compute this whole term and then subtract the KL divergence as a completely separate term in the loss function. So unlike in the PPO algorithm we covered before, here the KL term is not rolled into the advantage, and instead it's a separate penalty. And again, this thing can be dropped in many cases without contributing to quality loss. So if you drop this term, it basically is encouraging more exploration of kind of different outputs without tying the model down to the SFT model. But again, it also could decrease or increase a chance of degeneration of outputs. So it's a hyperparameter. All right, any questions so far? Not too different from PPO. We've just removed a lot of things, the reward model, the value function, and we've introduced this concept of a group and getting all the baseline and stuff from the group. Now, you might be thinking, okay, but I still have this RXYI, right, which we've so far discussed as coming from a reward model. So let's talk a little bit more about this concept of a verifiable reward. So in the simplest case, these can be like binary 0 or 1 rewards. You could use them to measure things like correctness, proper formatting. If you're doing like code generation, this could correspond to whether or not the code you wrote passed some unit tests or things like that. So there's, surprisingly many tasks where you can assign kind of verifiable rewards. But of course, as the task gets more creative and longer and more complex, it becomes harder to implement such a reward. It doesn't have to be binary. It could be like graded by some simple rules. So for example, with math, you could have either a binary reward or some softer reward where perhaps with that addition example, you have a reward where like how close you are to the correct answer is, so your reward is a function of the closeness rather than exact correctness. Still don't need any fancy reward model to do this. So let's take a simple example here just to make sure everyone's on the same page. Compute 219 plus 408. Let's say that's our prompt. Then we can implement a reward which is if y equals 627, this gets a score of 1, and otherwise it gets a score of 0. So this is an example of a correctness reward. Obviously, we don't necessarily want to just train language models for addition. That's a very inefficient use of all of those parameters, right, when you could just use a calculator. But as a math problem gets more and more complex and goes beyond something that you could solve with simple tools, you can still use reward like this. And similarly for coding. Okay, so in the last couple minutes here, let's get to the kind of how we can elicit reasoning behavior through this, this kind of formulation. So the other novelty in this DeepSeek paper was this idea of thinking tokens, which allow the model to perform reasoning before producing the final answer. So thinking tokens form essentially a special subsequence of the response y used for reasoning. And so if we had, like a simple example here, let's say our prompt is let 2x plus 5 equals 17 solve for x. And we might have some example of put your thinking steps between think and think tokens. So these are special tokens, and box your final answer. Like sometimes you can actually just say format your final answer in this particular LaTeX box or whatever. But basically, there's two different parts of this prompt. So this is the problem, and this is the thinking request and format. So if we just took a normal pre-trained language model, this second part would be basically just asking the model to do chain of thought reasoning before producing the answer. But now, as we'll see, we can actually use this, do training with this kind of chain of thought. So if we were to generate a response y, the ideal response would have something like this, where we open with one of these special tokens. Maybe it has some thought process. Well, okay, so 2x plus 5 is 17. That means 2x equals 12, so x equals 6. And then maybe at this point, because this is a simple problem, it ends its thinking. It produces this answer tag and just says 6, and then ends the answer tag. So if we got a response that looks like this, now we can compute the reward only over the final answer. So note that the model could produce absolutely anything it wants in between these think tags. The only thing that we will be evaluating is whatever is in between this answer tag. So as long as the answer is correct, that actually means that the thinking tokens are still part of the backprop, right? So if we get y that has a positive advantage, right? Maybe only one of the responses in the group was correct and all the other ones were wrong. We're not only going to increase the probability of producing the specific answer, but also of producing all of the tokens in the thinking tags, right? That were part of the process that led up to computing that answer. So that's the general idea. Okay, any questions about this, this setup here? Yeah.
So these tokens can be empty, or they're just like some like on tokens that you use in.
Are you talking about these think tokens? Yeah. They're special tokens that are part of the vocabulary, just like EOS or start of sequence or things like that. Yeah. So one thing to emphasize here is that your SFT model already at some percentage of the time has to be able to use these tokens correctly, right? It has to be able to produce responses that are in the correct format. Oftentimes we'll have a separate format reward, which is like 1 if the response followed the correct format with think, some tokens end think, answer, answer, and answer, and 0 if it doesn't. You can also combine the format reward and the correctness reward. So basically, if a response is not following the correct format, even if the answer is correct, you can give it no reward. So there's many ways in order to do this reward combination. Yeah.
So does the verifiable reward like follow like a binomial distribution then?
What do you mean?
Like you mentioned that it was like binary and that it was like 0 or 1. So like and when you compute group relative advantages, like you would be, I guess, would that be like drawing from the binomial distribution, like?
Well, it depends on how good your model is doing at that particular prompt, right? So if the problem is really hard, it could be that none of the answers that it generates are correct, right? And all of the rewards would be 0. If the problem is like hard but manageable, it could be that only one of the responses in the group is correct and gets a positive reward. And so one reward might be 1 and all the other ones could be 0, right? And so it's not like drawn from a specific distribution. It's all dependent on the difficulty of the task and the capability of the model at that point in time, if that makes sense. Okay, so, oh, yes.
How can you like enforce logic throughout the thinking? Like what if it's thinking through, still gets the right answer, but the whole thinking process was still like kind of incorrect?
That's a great question. So you essentially, in this setup, you can't. So the thinking process is not guaranteed to be faithful to what the model is actually doing. It could even be misleading. We see many cases where the model will follow one chain of reasoning in the thinking tokens where it gets to the right answer, and then the final answer is completely wrong. So it's not clear what happened in that kind of setup. Generally, this decreases as the model gets better and better, or bigger and bigger. And also, you can, and we'll talk about this in the next class, add what's called as process supervision onto these thinking traces, where you might give it a positive reward if it reached some like intermediate value or something like that during the reasoning chain. Yeah.
Yeah, so how do we find the G different responses from the, are they just like sampled from the?
Yeah, each of the G responses is just sampled from the policy model.
Okay, so they're like, are they like the most probable results, or is there like?
Not necessarily. They're just sampled using one of the sampling algorithms. So
Right.
Ideally, there's a lot of diversity there.
So what do we do to like make sure like we don't have the same thing twice then?
In general, you don't do anything.
Okay.
Yeah, and it's actually good because you will measure the you'll have a better approximation of what the model thinks is likely. So I wanted to end really quick with two figures from the DeepSeek R1 paper. So this plot here is on the y-axis showing the average length of the response. So this is including both the thinking and the final answer. And on the x-axis, the number of steps that the model, like the number of gradient steps. So you can see that there's a clearly increasing trend here, where as you train this model to maximize the reward, it is using more and more thinking tokens before getting to the final answer. And this plot shows that the accuracy is increasing at the same time. So as the model is thinking more, it is getting better and better at these math problems. And the final thing that was kind of very exciting to see from this paper is what they call an aha moment during the thinking process, where you can see this question here, and here's a response. It starts with the think token, it does this stuff, and then it's like, wait, let me reevaluate this thing, and then it backtracks, tries something else, kind of like identifies that it did something wrong initially, and finally it produces the right answer. So some kind of properties of these reasoning traces that people like to see are like backtracking, explaining what it thinks it's doing, planning, some sort of structured planning to, like, here's the steps I'm going to take to solve the problem. You've probably encountered a lot of these while interacting with GPT and other language models. So anyway, we'll start here with the next class and kind of dig deeper into these reasoning traces and what you can use this algorithm for. So see you then.